Good morning, everybody, and welcome to my talk, Orchestrating Robot Swarms with Java. Let's let the last few people sit down, and then we'll get straight in. So, I'm going to start by telling you the problem we're trying to solve at Ocado Technology, and that's the problem of grocery e-commerce. At Ocado Technology, we create an e-commerce platform which allows consumers to go online and buy their grocery shopping. They can put together as many things in their basket as they want, and typically our customers will put up to 50 items in their basket. This will be a range of products off the shelf, maybe baked beans, some products from the fridge, maybe some milk, some products from the freezers, maybe some peas or some chips. And then when they've decided what they want and what they want to get delivered, they can choose a time slot. We offer 1-hour time slots, anywhere from 5:30 in the morning to 11 o'clock at night. And they can say that they want their shopping delivered in this precise 1-hour slot when they know they're going to be in. So that's very briefly the problem we're trying to solve at Ocado. It's quite simple to state, but to do this in a profitable way is quite difficult. So we are the world's largest online-only grocery retailer, and we have at the moment about 720,000 customers in the UK, but we are going global. We offer our customers about 55,000 different products, and the main thing which differentiates us from other grocery companies is we don't have any shops on the high street. So we do all of our fulfillment from highly automated warehouses, and it's about those warehouses which I'm going to talk to you today. So this is just a slide showing some of the customers we're going to be working for in the future who have signed deals with us at Ocado. So you can see along the top line, there are businesses in the UK that we've had for nearly 20 years. And then at the bottom, a selection of international grocery companies who are going to start using our robot warehouses to deliver groceries to their customers in their countries. And so this is a video of the system that I'm going to be talking about today. So this is a video of our warehouse, one of our warehouses in the UK. And everything you see on this video has been designed and built by Ocado Technology. So the hardware, the robots, the grid structure, the track that they're running on, the software which controls the robots, and our air traffic light control system, which I'm going to talk a lot about today. What's not so clear from this video is that these robots are on a structure which is about 2 stories high, about 7 meters. They're about the size of a washing machine, so they're about that big. And they're picking up containers full of products, and they can pick up about 35 kilograms at any one time. You might be able to see it. When they stop, they pull up the container inside the body of the robot, and then they whiz around to take the products where they want to go. So this is me. I'm a technology lead at Ocado Technology. I've been working at Ocado for about 3 years, and I've been working to help develop this system. If you're on Twitter, then you can follow me at Boffelot. So this is a very brief diagrammatic overview of the system I'm going to talk about today. And there's 3 main aspects which I want to talk about. There's a Java-based control system which runs in our data center. This is our air traffic light control system, which is controlling the thousands of robots at any one time, telling them where to go, what to do, make the most efficient use of them. To control such a vast number of wireless devices in a small space, we had to develop our own 4G-based wireless technology. So things like Wi-Fi just are not suitable for the real-time communication needed to control this vast number of devices. And then we also, like I say, created the custom hardware and software, which is the robots themselves. So my talk this morning is split up into 3 main parts. I'm going to talk to you first part about simulation and determinism and why that's important for us. I'll run through some of the optimizations we've made in our Java-based control system. This is a very high-performant, low-latent piece of software, and our use of Java has kind of faced us with some unique challenges that we've had to solve. And then I'll present a case of how we use Java to actually test the software on our robots, which is embedded C software. So how many people here are familiar with simulation, or what simulation is? I see one or two hands. That's a typical response. I find that not many people have come across the idea of simulation. So this is the first line from the Wikipedia article, and I've put my highlighting in bold there. So simulations are approximate imitations of some process or system in the real world. And to create a simulation, you first have to decide how you're going to model the real world. So to give some examples, some people may be familiar with these games, Microsoft Flight Simulator and The Sims. I had to update my slide literally just 2 days ago, because I don't know if you've seen the new Flight Simulator video, but it looks pretty awesome. It's the first update they've given to the game in about 13 years. But that's a great example of where they've created an approximate model of the whole world. Right? And they've gone to a level of detail which is necessary for flying, so you get great over aerial views, but if you go like right into the city, you're not going to see people walking around doing their shopping. Whereas The Sims is looking to model processes on a day-to-day life, and so yes, they've gone to the effort of modeling what a human is like walking along the street. Again, an approximate model to simulate the real world. So the question is, why do we use simulation at all at Ocado Technology, and why do we use simulation in this scenario? And the main answer is because we're dealing with hardware. The fact that we're dealing with hardware means that any changes that we want to make to our software, if we want to do it on real hardware, can be really expensive. It can be slow, time-consuming, you need to buy the hardware. And so simulation lets us do mainly 3 main things that we do with simulation. We can test our software against simulated hardware. We can research new algorithms. So if we want to try some new software to see if it's more performant, we can test that against our simulation. And we also verify our warehouse designs. So when we're designing a new warehouse, we want to validate that it is going to do the right throughput that we think about. And so we can use our simulation to help us verify that our warehouse designs are accurate and will do what we suspect. So I'm going to talk a bit about the sorts of things we simulate in our system. So if we are talking about our Java control system, which is controlling all of our robots, then we will simulate basically everything around that software. So the first thing is we will simulate other software systems. We often run our simulations for many days, so days to weeks worth of real-time production, because we want to see how our warehouses perform, say, over a week. It's not good enough for us to see how they perform just over 2 or 3 hours. And so to do that, we can't just stub out or mock our external software dependencies. We have to create a simulation so that we can run it with the numerous number of inputs and outputs that you might get from running in production over many days. We simulate hardware. So a good example is the robots themselves. So again, this allows us to test and research without having to have any real hardware. So we have a simulated model of what the robot does, how it moves, how it functions. And we also simulate people. Believe it or not, we still do have people in our warehouses, even though they're highly automated. And so we simulate their processes and how they interact with the system. So this gives us a complete model of our warehouse, which we can then run our production code against to test if it's working performantly and whether it's doing what we expect it to do. So here's an example from our domain of what we might simulate. So this is a graph of time versus speed, and this might be the graph of how a bot moves in one direction. So you saw from the video, our bots can either move in the X direction or the Y direction. And this might be their speed profile as they move along. So they start at 0 speed. They take some time to get up to constant acceleration. They have a top speed, which they can move at. Then, when they come to start to slow down, they have some constant deceleration until they come to a standstill. Now, the change in acceleration that you see at these points here, here, and here, that's called jerk. And if you try and model this mathematically, There's several simultaneous differential equations, long multi-page solution of how you solve these equations. And we don't really want our developers to be solving really tough math problems. So we might model our bot movement with this red line. So rather than modeling the precise movement, we might say that it just moves with some constant acceleration, a sharp change into the constant speed, and then sharp change into constant deceleration. And so for the purposes of testing our control software, this is perfectly adequate to give us a model of how the bot moves and an approximation of how the system is working. So a particular type of simulation that we use is one called discrete event simulation. Again, this is the first line from the Wikipedia article. The main thing I want to draw your attention to here is this bit down in the corner. The fact that we can jump in time. So I mentioned that we like to run our simulations for many, many days, maybe even weeks. And if we had to do that in real time and kick off a run and wait 2 weeks to get some results back, that's really inefficient. We want our developers to get fast feedback about their code, their new algorithms, their designs. So this form of simulation allows us to run our code much faster than real time. And so I'll demonstrate that with an example. So here, simulation time is sort of the time in the discrete event simulation, and real time is the time you'd see on the clock on the wall. So the red little thing there is, say, a bot might be broadcasting its position information. We can use that simulated model just before that I showed you to calculate what its position might be. And then our real production software will receive that event and perform some action on it. And that action will take some time to execute. And then the next event will come along at time t. So the main thing here, that rather than waiting for time t to pass in real time, we're able to jump in time in our discrete event simulation and start processing that next event straight away. So you can see this goes on and on. More events come in. We keep processing them. And the end effect is that in this example, we've been able to process 3 t's worth of real time in just under 1.5 t time in real life. And so this is super powerful for us because, like I say, it allows us to run our real code in real scenarios, but much quicker than we would if we had to wait for it to run in real time. So linked to our discrete event simulation is this idea of determinism. And fundamentally, real-time systems like ours just are not deterministic. There are many aspects of it which mean that you can't run it repeatedly and get the same result. The time, for example, only goes in one direction. That's not deterministic. Issues with event scheduling or kernel thread scheduling things mean that if you're running a real-time system, you're not guaranteed to get the same result again and again. And this can make debugging for our developers really quite difficult. And we really want determinism in our discrete event simulations. Like I said, primarily because we use our simulation as a research tool for researching new algorithms, but also for testing new designs. So our developers are running these in the office, and if something goes wrong, they're going to want to run it on their desktop, debug it, and be able to run it again and again and again and make sure that they get the same result. So determinism is really important for us. So important that we test for it in our CI pipeline. We do that by running the same test again and again and again and make sure we get the same results. It's not guaranteed to prove that our code is deterministic, but our experience has shown us that any small amount of undeterminism quickly spreads within your code. So there's 3 areas I'm going to talk to you about where we've had to write some of our own abstraction layers or do something special to make sure we get determinism. And that's in time, scheduling, and iteration. So firstly, I'll talk about time. Like I said, the time on the clock on the wall is not deterministic. So if you're using a call like system.getCurrentMillis in your code, if you run that in your tests, you're never going to get the same result back from that call. So to get around that, in our software, we've had to introduce our own abstraction, which we call time provider. It's a pretty simple abstraction. It literally just has one method called getTime. But the benefit of this is that in our discrete event simulations, we can have an implementation which looks like this, the adjustable time provider. So you can see that we've got the getTime method, which is overridden from the interface. But most importantly, we have the setTime function, which is what enables us to do that jumping in time that I mentioned and showed in the example. And then, this is simple Java stuff, but the benefits of having interfaces in different implementations is that when we want to run this in real time in our production code, we can just sub that implementation for one which does call into current time millis. So scheduling is another area where we had to address determinism, again, because the standard libraries you get in Java, the standard classes like executor and executor service, they're just not deterministic by default. And so again, we've had to introduce our own abstraction to get around the fact that these classes provided to us in Java are not deterministic. So here are some sample interfaces from our code. I've pulled out the kind of fundamental methods, which are the crux of these classes. So we define an event. An event has a time it needs to run, a run method and a cancel. And then we have our own scheduler, which allows us to schedule events now and schedule events in the future. And then again, just like in the time example, we can have different implementations for both our discrete event simulations and our real-time production code. So this is an implementation of that event scheduler, which we use in our discrete event simulations. And hopefully you can see, we'll step through it in a minute, that this was exactly that example I showed you. So we have an event queue. This is all the events that we're going to process in time. And while that queue is not empty, then we can use our time provider. Here you can see it's the adjustable time provider to set the time, and that's our jumping in time that I showed you when we were stepping through. We can run the event, and then when it's finished, we just get the next event and go around the loop. The last area is determinism. For determinism is around iteration. So here's a quick question for you. Have a look at this piece of code. Set.of, I think, was introduced in Java 9, one of the helper functions. Does anyone know, is this deterministic or not? Anyone going to be brave enough to shout out yes or no? The answer is it's not deterministic, and we know that because you have to go and read the documentation. If you go to the Java docs and read set.of, you'll see this line: the iteration order of set elements is unspecified and subject to change. So the library creators are telling us in their documentation that this is not deterministic. And so that's an issue for us. We can't use these methods in our code if we want deterministic behavior. Here's the same example with just a slightly modified set implementation. This is a mutable set from the Google Guava library. And probably no surprise that this is deterministic. And again, we only know that because we can go to the documentation and read what the library creators are guaranteeing for us. And so you find this line: except for sorted collection, order is preserved from construction time. So we're guaranteed, in this case, to always get deterministic behavior. So that was a quick run-through of some of the concerns we have around our simulation and having deterministic behavior. And I want to move on now to talk about how we have tackled the creation of our Java-based control system and the optimizations we've had to introduce to make it performant. As you can see here, it communicates with our robots 10 times a second, and it's communicating with up to 1,500 robots at any one time. So it really does need to be a very low-latent application to make sure the robots get their commands in real time and they can execute work when we want them to. So this quote is quite important to us, and I'm sure many of you have heard of it. Premature optimization is the root of all evil. And this kind of sums up for me what we believe at Ocado when we're doing the development of our systems. I'm going to show you quite a few optimizations that we've done, but I want to really stress that the optimizations that I'm going to show you are not things that we do throughout our whole code base. They're the things we do in the most performance-critical parts of our code. And I think it's better to show the quote in a bit of a wider context. So we should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil. Yet we should not pass up opportunities in that critical 3%. And so, yeah, really want to stress that what I'm going to show you now is that critical 3% for our application. It's the areas where we've measured, found areas for improvement, and have done some optimizations. So the first area, again, is around event scheduling. I said that previously that the executor and executor classes are not deterministic. But we have some requirements in our system that we need to schedule events for specific times. So we need to be able to maybe tell a robot at 10 seconds in the future that it needs to do some command. We need to ensure that these events don't get delayed. It's no point sending that command to a robot 1 second too late when we wanted it to do some work. And we also can't let any of our events back up. Again, because this is a real-time system, and we want our robots to be always getting the commands just as they need them. So who is familiar with this class? Maybe some of the older Java developers in the room. If you have those requirements, you may look to this class if you were working in Java 5 or something. But if you're a modern-day Java developer, hopefully you would maybe go to a class like Scheduled Thread Pool Executor. To meet these requirements that I just stated on the previous slide. And so that's what we did to start with, but we quickly found out that it didn't meet all of our requirements, and I'll talk through why that is now. So it does meet the first requirement quite clearly. It says it in the name. It's a scheduled thread pool executor, so we can schedule events at specific times in the future. But let's think about the second requirement. Individual events can't be arbitrarily delayed. Well, when you schedule an event in the thread pool executor, and it comes time for that event to be processed, you can't actually control too much what it's going to do. Depending on your config parameters for your thread pool size, your min thread pool size, or your max thread pool size, maybe the thread pool executor is going to decide, hey, I need to create a new thread now. And so if it decides when it wants to process your event that it needs to create a new thread, well, that's going to introduce some arbitrary delay into our system. And so that means that implementation doesn't meet this requirement for us. And similarly, on the third requirement, if you dive into the implementation of the scheduled thread pool executor, you'll see that it's using an unbounded queue for its queue of events to process. Now, being an unbounded queue, what that means is that queue can just grow and grow and grow, and we wouldn't necessarily know about it. So if we're scheduling events too quickly and our system can't process them fast enough, then this queue of events inside our scheduled thread pool executor is just going to get bigger and bigger and bigger, and hence our third requirement is not satisfied either. So we learned this the hard way. We implemented it. We ran our performance tests. Our performance tests are run using the simulations that I talked about earlier. And so we had to come up with a different method. And so we settled on this idea of a busy loop. Is anyone here familiar with a busy loop or a wait loop or spin loop? They're sometimes called no? Okay, cool. I'm glad I'm teaching you something this morning. So this is what a busy loop might look like in the implemented as a concrete implementation of our event scheduler interface. So you can see this looks very much like the event scheduler we had in our discrete event simulation. We have a queue of events. We have our time provider. This time, the interface is going to probably be the real implementation, calling current time millis. And rather than running until the queue gets empty, we run this loop forever and ever. And every time we come around the loop, we check if the next event is ready to be processed. Basically, is it time to run this event now? No, okay, spin around. Is it time to run this event now? No, spin around. Is it time to run this event now? And it just does this, goes around, and that's how we process our events. So you might wonder why we do this. And if you go and Google this on the internet, you'll often be told you shouldn't do this. Because in most cases, this is terrible. You're using up way too much CPU. You could be using that CPU to process other events. And in general, it's kind of classed as general bad practice. But we settled on this because we tested it and found that it gave us some performance gains. So the advantages that we observed in our system when we ran our performance tests was that we were able to get the latency of processing events down from about 5 milliseconds down to effectively 0. Because as soon as the event is put on that queue, the loop is ready there and it goes, right, I can execute it, and it goes and executes it straight away. So you have one core, one thread, constantly just dedicated to checking events, which means you can drop your latency much lower for processing events. And with that reduced latency meant we were able to get, in our system, 3 times higher throughput of events. Now, I'm not saying you will get this in your system if you implemented a busy loop, but in our system, measured in our performance tests, this is what we were able to observe. So this is an optimization that we adopted and have been using for several years. But everything is a trade-off, and this comes with some disadvantages. You get 100% CPU utilization. You can no longer look at your CPU utilization to see how well your application is performing. It's 100% all the time. We have about 4 or 5 of these in our application, so constantly our CPU graph is 400, 500%. So we have to use other sorts of monitoring and measuring to see actually how our system is performing. And depending on what processor you use, that 100% CPU utilization can actually reduce your clock speed over time. So the CPU running at 100%, generating all that heat, can actually over time degrade the CPU. But that's a trade-off we were willing to make. Caching is another area where we've performed some optimizations in our system. We have 2 main types of caching in our system. And the first one I'm going to talk about is memoization. So this is where you compute a function for a pure function, a function that is where the output is just the result of its inputs, and you cache the result. So the next time you call the function, you don't have to incur the cost to execute that function. We're quite greedy about how we perform this in our how we do this in our software. As I mentioned, everything with optimization is a trade-off. So we don't wait until the first function call to cache the result. We will, in startup of our application, actually compute lots and lots of common calculations that we know we're going to perform throughout the life of our application. So we incur a cost at startup time to perform these hundreds, thousands of function calls with varying different inputs, and we cache the outputs so that when it comes to the latency-sensitive part of our code, when we have to get a command out to our robot in time, then we can use the cached results to make parts of those calls quicker than we would do if we had to actually compute the function. Another sort of caching we do is object caching. So the creation of objects is not expensive as such. It's very cheap to call new object now in Java. But excessive object creation actually has quite a negative impact when it comes to garbage collection. It puts a lot of pressure on your garbage collector if you are generating lots of objects. So in a similar way to what we do in our memoization, we're very greedy about object caching where we can be. So one example of this we have a coordinate class in our system. So no surprise, you saw our robots are running in X and Y, and we have a class which has 2 fields, X, Y. We call that coordinate, no surprise there. And our grid is of finite space. So what that means is there's only a finite number of coordinate objects that could possibly exist. So in this example, what we do is, again, at startup time, we will create and cache every single possible coordinate class. It's a class that we use so much through our application that by creating all the objects up front, they're immutable objects, so we can share them across threads quite safely, we can then just use these objects with a simple cache lookup throughout the life of our application. And this reduces quite the pressure on our garbage collector, reducing pause times, which is really significant for us. To find out all these places where we can do optimizations, we have to profile. We have a CI pipeline for tracking the performance of our simulations. And when we see some unacceptable performance, it's on a developer to go and pull that code up on their machine and start profiling it. You can use your favorite profiling tool. And if you're not familiar with JMH, then I would suggest you go and read it, because JMH is a great tool for doing micro benchmarking. And it's a tool we use a lot to test small changes to our code to see if we can get performance gains. So that's from the JMH website. It's a great framework. It will stop you from falling into all of the pitfalls that you might fall into if you're doing micro benchmarking around timing and JVM warm-up and things like that. So here's an example of some code where we ran through a profiler and found how to optimize it. This is an example of some JMH benchmark, literally just calling compute if absent on a concurrent hash map. And we ran this, and we weren't seeing the performance we liked. So someone thought, okay, what happens if I myself check the result before and then call compute if absent? Again, I'm going to caveat this by saying I wouldn't suggest you do this in all your code. I'm not saying you should go out and replace your compute if absent with this block of code. But in our scenario, when we tested it and in our application, we were able to see an almost double, 2 times increase in the throughput of our function. So JMH is great. It's a great framework. I'd really suggest if you're not familiar with it, you go out and read about it, for allowing you to test these small bits of code and seeing where you can get some real performance gains. Probably no surprise that we're using Java is that garbage collection is a big issue for us. And it's our primary source of all of our application pauses. Oh, jumping ahead too fast there. So the problem with, like I said, with garbage collection is if you create too many objects in your application, you put a lot of pressure on your garbage collector. So we have gone through in some of our performance critical code and done things like removing optional from APIs, using for loops instead of streams, using arrays instead of data structures like hash sets or linked lists, and not doing things like primitive boxing or unboxing. Again, I stress these are not things I would suggest you go out and do all the time, but in performance critical code, these things all have in common that we have basically reduced the number of objects that we would be creating in some bit of code. So optional is a great class for displaying intent, and you should use it as return types from your functions. It makes your code more readable, but it does create an unnecessary object. So if you're in a function which you're calling lots and lots and lots of times, those object creations can add up. Similarly with all the others, the streams API creates lots of objects, linked lists are lots of objects. So when you need some performance gain, you often have to revert back to older style patterns like the simple for loops and arrays to avoid that object creation. So some tips for garbage collection are, hopefully lots of this is obvious to you, enable GC logs by default, investigate the different collectors. We have quite a few different garbage collectors now, and the latest one isn't always the best for your application. So understand how they work, what they do. The parallel throughput collector, for example, is still probably the best collector if you're doing batch type jobs. If you're maybe running an overnight batch and you need to just get it completed as quick as possible, the throughput collector gives you that throughput which, say, G1, GC doesn't give you. But we were really interested in garbage collection for our application because, like I say, it's the primary source of all of our pauses, and we want to get those pauses down as low as possible. So when ZGC came out, we were really curious to find out if it would give us benefits. So if you're not familiar with these garbage collectors, G1's been around for 10 years now, was an experimental option in Java 6. It's great for us because you can specify the pause time. So we've been using this in production to set the maximum pause that we are comfortable with. But you trade off that guarantee with higher use of your CPU because it's using some threads concurrently with your application. ZGC, on the other hand, was introduced in Java 11. It's still an experimental garbage collector. You still have to unlock the experimental options if you want to use it. But the big draw is that it's aiming for pause times of at most 10 milliseconds. So when we saw this, we got super excited and was like, right, can we use this? Can we test it? And we used our simulations to run some tests. And these are the results that we got. So along the x-axis is percentile of pause times. And on the y-axis is the actual pause time on a logarithmic scale in seconds. So if you look here at the 95th percentile, what's that saying is 1 in 20 calls in ZGC were greater than about 50 milliseconds. That similar point for ZGC is somewhere over here. Something like maybe 1 in 100, 1 in 200 calls are greater than, pauses, sorry, are greater than 50 milliseconds. So this is a massive win for us, and it's one of the reasons why we actually use Java. It's because we can get these performance gains for free from the evolving platform and the evolving JVM. These same results are seen here in throughput. What this is basically saying is that for G1 GC, we had a 12-hour test, and so for 7.5 minutes, we were actually paused doing garbage collection, whereas in ZGC, that was like 1.5 minutes. So a 5-time reduction in pauses, just from changing our garbage collection and moving to the latest version of Java, which is pretty great, in my opinion. So that's everything I wanted to say about the optimization, some of the areas we focused on to do optimizations in our control software. And for the last few minutes, I want to quickly run through maybe a bit of more of a novel use case of Java. And this is how we use it to test the embedded C software that runs on our robots. So our robots are embedded devices. We are using embedded C to run on chips. But we want our developers to be able to test in the office. And we've created a Java simulation framework to allow them to do that. So here, if any of you are familiar with doing embedded software, testing it can be slow. We want all of our developers at Ocado to be following agile practices and continuous delivery. And so in this example, we're not optimizing for application performance. We're actually optimizing for developer productivity. And so getting fast feedbacks from tests is really the name of the game here. And we want all of our C developers to feel just like our Java developers. We want them to have the greatest tools, the best IDEs, to be able to run their code from their desktop and not get envious of their kind of Java colleagues. And no surprise, we use simulation to help address these problems. So this is another diagram of our system, with the control system on the left communicating wirelessly with the robot on the right. In the simulations that I was talking about before, when we were testing our, running out of time. So these are some of the things you'll get in a robot: some PCBs, motors, batteries, sensors, everything that makes up the robot. Sorry, did you want a picture? Oh, there you go. In the previous examples, when we're testing our control software, that whole robot is simulated. So when I showed you the graph of the simulated time and speed profile, and all the other functions of the robot completely simulated. In this case that I'm talking about now, we want to test the robot's software. So one way we could do that is to simulate those parts in red. We could run all of the real software and just simulate the hardware, simulate the PCB, simulate the motors, the batteries, the sensors. That's one valid approach, but that's not what we've actually chosen to do. We've chosen to do this for testing our robots. So simulate absolutely everything apart from the core application logic. And why did we do this? Well, like I said, what we're optimizing for here is developer productivity. And we analyzed what our developers were doing and found out that this bit of code in green, the application logic, this bit here, that's the bit that the majority of our developers are working on. And that's the bit of code that is changing the most. The other bits of software actually might be from third-party vendors or things we created once, DLLs or hardware driver interfaces, and they don't change much. So there's not much benefit in running the real version of them. By doing this, we get the most benefit for testing the software which is changing the most rapidly and has the most developers working on it, so optimizing for developer productivity. And using a Java simulation framework, and actually the same Java simulation framework that we use for testing our control system, means we can run integrated simulations. So we're able to run the real version of our air traffic control system along with real versions of the robot application logic. And across many JVMs, we can run this massive integrated simulation testing the real integration between our robots and our control system. And we can do this all from the office. We don't need hardware. We don't need a lab or test equipment. We can do this all on servers in our data center, getting that fast feedback to learn about how our system's working. And that's extremely powerful for us. So running out of time, sorry, I'm going to just speed through this last bit. So how does this work in practice? If you've got some Java code and you want to work with some C code, well, if you've done C development, you'll know you'll generally have a header file. You need to convert that header file into a class file. And often you might just have a developer who's doing that manual conversion. That works. If you have multiple header files, then sure, maybe your developer can sit there and manually bash out a few respective class files. But when you're working on a big C code base and you've got hundreds of header files, are you really going to make a developer write all those class files? You don't want your developers to get fed up of their job and go and leave. I said this is about developer productivity, about making our developers productive and happy ultimately. And so we turned to some great open source tools. It's power of the open source kind of idea. One tool being JNarrator, this one down here. Basically an automated tool for taking header files and creating class files. And then another library called Bridge, which does a lot of the C and Java bindings, so you don't have to bother doing that. And I just mention these again because, like I say, the name of the game in this example is developer productivity. So anything we can take from open source to help our developers get their jobs done quicker is a win for us. So I'll talk briefly about the setup and some of the challenges, and then we're at the end. So our C firmware is compiled into static libraries, SO files. We compile these static objects into 2 exe files. We happen to have 2 chips in our robots, 1 exe for each chip. We've got some C++ code too, and we use Java for test cases. And we use Java for the hardware simulation as well. So our developers, our C embedded developers, are writing Java tests using the frameworks like JUnit and mocking frameworks and all the great stuff there from Java to test their embedded C code. And so this is one way how we integrated our C and Java code. We ran our C code externally in separate JVMs. And we ran all of our test stuff in one JVM with some comms library there in the way. This was the easiest way to set it up for various reasons around like sharing memory spaces in your C code. You can also do things here like simulate a chip restart. Because this is running in a separate JVM, you could just restart this JVM, for example, and that simulates resetting a chip and having the code come back up. And this worked for us for a while, but we found that these links here, this communication, which on the real chip is actual hardware buses, so actual tracks on your PCB, when you're putting this over a network, turns out this runs really slowly. So we moved to a different option where we ran everything in one JVM. So we have our Java tests, we have our real code in the middle, and then we have our hardware simulation at the bottom. And this works well, but it has some downsides as well. One of the main downsides being if you use JUnit 5 and parameterized tests, then you're restarting this JVM every single time you're trying to test a new parameter. And again, your tests then run really slowly. We want to use parameterized tests because they give us power. They let us test a wide parameter space really easily. And so what we had to do was ultimately adopt both approaches for different types of tests. And so finally, some challenges we faced in doing this. Garbage collection is, well, if you do this, is only limited to your Java code. So your C code can return some unsafe objects and basically crash your whole system, so that you have to be careful there. So yeah, it can pass back arrays of the wrong length or badly formed objects. If your C code asserts, then that crashes the whole JVM, which is not great either. You don't get some nice stack trace. It just bums out with a seg fault. So we've had to introduce some of our own abstractions again, like in the time example and the scheduling example. Here we've had to introduce our own assertion abstractions so that we can actually test our C code throwing asserts. Because we're running this mostly in tests, JVM startup time is a problem. That's something we optimize. Again, we want our developers to have fast feedback, and so bringing down the JVM startup time is really important for us. And as I mentioned, kind of work with JUnit 5 and parameterized tests has thrown out some challenges. So whiz through that just in time. So in summary, at Ocado, we're solving the problem of online grocery and getting that to our customers. And we're using Java in our warehouses to control our robot swarms, controlling up to 1,500 robots at any one time. We use simulation throughout our whole development pipeline, and it's really important and powerful to us. We've had to introduce many abstractions into our code that don't exist in standard Java libraries, mostly to satisfy our need for determinism. And like I said, I ran through a brief example of how we use Java to test some embedded C. So I started with a video of our real robots. I'm going to end with a video of our simulation for you. So this is a visualization that we've created in-house. So what you can see here is this is our real production software controlling 1,000 robots, but our robots here just happen to be simulated robots running on a different server in the data center. And so we can use this to analyze, to get insight into how our system is performing. We make heavy use of colors to distinguish what the robots are doing. Here you can see them winching and dropping things off. We don't have a model of pickers, but here there would be some humans in a real warehouse moving objects between the containers. And this is a tool we use every day and develop in-house as well. So that's the end. I've got 1.5 minutes to take any questions. Thank you for listening. I hope you found that insightful and interesting. And I'll be around for the rest of the day if you want to kind of grab me and find out more. Thank you very much.